Um, so, Good evening, everyone. Welcome to week 11 problem solving session. My name is Bhavya, in case you are attending for the first time. And today we'll be looking at the topic of recurrence relation and asymptotic complexity. Okay. And if you are from a mathematics background, then recurrence is an important part of your curriculum or your applications, and because it is immensely helpful in counting things. And as part of CS students also, if you are computer science students, then recurrences are equally important um, because it embodies the idea of recursions. We'll look at what recursions are. I think you've seen in the lectures also. Kind of embodies the idea of recursions and how problems can be solved in a more intuitive manner. Okay, and another important fact is asymptotic complexity. Okay, so asymptotic complexity talks about how we can, measure the efficiency of algorithms, not in the sense that how quickly it will work in a single computer or a supercomputer or a phone or whatever, but we can measure the complexity across all devices. It does not matter where we measure it. Okay, and not only does it tell us the speed of the algorithm, but it actually tells us the growth of the algorithm, the rate of growth. I'll come to it later, but I'm just giving you an introduction why it's important. It's immensely important in the world of algorithms and computer science, and recurrences too in the world of mathematics for counting. Usually, it's used for counting, right? So let us begin. Okay, what is a recurrence relation? First of all, a recurrence relation is a function that is defined by itself. Now, what do I mean by defined by itself? Your function definition will look somewhat like this: fn equals fn minus 1 plus 1. You can see, and if I ask you, okay, so what is the how is the function fn defined? You'll say, oh, okay, it's defined as fn minus 1 plus 1. And you might say that is kind of absurd because the definition of f depends on the definition of f itself, right? So the function is defined by itself, and we'll soon see that it is not actually absurd at all. Okay, it actually does make sense. An alternative way to see it would be as a sequence. What do I mean as a sequence? Okay, the sequence would be as follows: a0, a1, a2, and so on till an, where f of 0 is equal to 0, f of 1 a0, and f of 1 equals a1, and f of 2 equals a2. Actually, the other way around, a is 0 equals, but you get the idea, right? So an will be equal to f of n. Alternatively, we can see the function f to be like a sequence. Okay, so then this same function can be defined as an equals an minus 1 plus 1. Okay, so how will the function look like? Let us try. A of 0, say a of 0 is defined as 1. Okay, then a of 1 will be a0 plus 1 by definition, right? A of n minus 1 plus 1, which is nothing but 1 plus 1, which is equal to 2. What is a of 2? It is a1 plus 1, and we know that a1 is 2. Okay, so 2 plus 1, which is equal to 3, and you'll soon find out that the entire sequence, okay, is equal to 1, 2, 3, 4, and so on. Or, in other words, f of n minus 1, okay, f of n, the function f of n, could be written as, okay, this is f of 0, f of 1, f of 2, and so on, right? F of n could have been written as simply f of n minus 1. Simply as n minus 1. I hope you see it, right? Instead of defining f as follows, fn equals f of n minus 1 plus 1, f of n could have been written as n minus 1. And you can just cross verify and you can just cross verify, try substituting it online, and you will see that f of n is indeed this function. Okay, and this function, okay, is what is called the closed form. It is free of recurrences. No, but and why is it why is it nice? It looks simpler to us. We can easily calculate it. Okay, but calculating this may not be too obvious. You may go across like a huge ladder of values. Okay, so we would always want something like this. But the problem is that the real world is often defined in this way. Okay, so it may not be obvious to us that here in this example it is obvious, but in a lot of cases it is not obvious. Especially when we analyze algorithms, this is what we get. Okay, we get recurrences. This is let us call it the recurrence form. So what we want to do is we want to study algorithms or like counting scenarios, and then finally we bring in the closed form. We analyze the closed form, what it looks like. This is one way to see the application of recurrences. Okay, so yeah, let's move on. I hope that was a clear enough introduction. Okay, so how do we find the values of a recurrence? One straightforward way is called substitution. Now, what is substitution? Okay, in an, I will plug in the value of an minus 1. But an minus 1 depends on an minus 2. So I'll plug in the value of an minus 2. And in an minus 2 depends the value of an minus 3. And I'll just plug in values and so on. And finally, I'll just obtain an. Okay, how it works, I'll show you. For example, the question says the following. If an equals 2n minus 1 plus 4 and a0 equals 6, find the value of a2 and a4. Okay, this is the question. So this is a straightforward method. Given is an equals 2an minus 1 plus 4, okay, and a0 equals 6. Okay, this is what is given to us. Now what we do is find the value of a2. We are saying a2 is what? That is what we need to find. But according to definition, we know that a2 is just 2 of an minus 1. In our case, n is 2. In our case, n is 2. So 2 minus 1 plus 4, which is equal to 2 of a1 plus 4. Now what do? We have another another element in the sequence. So to simplify it, we'll just use this definition once again. Okay, which is equal to 2 of, okay, now instead of a1 we do 2 of an minus 1, right? So 2 of a1 minus 1 plus 4 plus 4. So you can see that this is getting expanded into this. We get 2 of a0 plus 4 plus 4. So now what do? Well, we could have continued doing this, but then we'll get minus 1. Okay, we get a of minus 1, and then we get a of minus 2, and then a of minus 3, and so on. But that process will never end. In order to stop the process, we have what is called an initial value, where the recurrence actually stops, so that we create a finite process. So the initial value says that a0 is actually equal to 6. So since a0 is equal to 6, we have a2 is equal to 2 times 6 plus 4 plus 4. What do we get? 2 times 6 is 12 plus 4 plus 4, which is equal to 2 times 16, which is 32 plus 4, which is equal to 36. Okay, the idea is simple. The idea is just that as soon as you find another function, then just substitute it using the definition again. That is the basic idea here. I hope that is clear. Okay. Now what are we saying is we found the value of a2. Now we want to find the value of a4. Find a4. So can you try your hand at it? So can you tell me what a4 will evaluate to using substitution method? Okay. Okay, this guy is pretty good. E4 equals 1. Okay, we'll see. Divya. Good. Okay. Others, please try finding A4 using substitution. Okay. Note that A0 is equal to 6. Maybe so that you see the process. Okay. Divya has written A4 equals 156. Yeah, that is correct, Divya. So I'll show the others how it's done. Okay, good. Um, so again, just follow the definition. Okay, what's written in the definition is 2a n minus 1 plus 4. So 2a, n is 3 in this case, minus 1 plus 4, which is nothing but 2a2. Sorry, what am I doing? 3 plus 4. Okay. Now further expand this because we don't know what a3 is. So a4 is nothing but 2 times 2a2 plus 4 by definition, right? And now, well, one thing you can do is you can keep expanding a2 to until you get a0 like we did earlier, but we already know a2, already know a2. How? We just calculated it here. We just show that a2 is actually 36. So yeah, let's just plug in the value of 36. It should work, right? Because even if I expand this, I'm just going to get 36. So what I'll do is 2 times 2 times 36 plus 4 plus 4. So how much do I get? 2 times 36 is 72 plus 4, which is equal to 2 times 76 plus 4. Yeah, which will give me some 2, 15 plus 4, which is equal to 156. Okay. Please stop me if it was not clear at any point. Okay. So the idea here is that you can reuse a2, the value that we found out here. Well, you can just continue expanding also, but it may be a bit more work that way. Okay. So let's move on. So now we are interested in solving recurrences. Okay. What do I mean by solving recurrences? I mean finding closed forms. I showed before that closed forms are those equations that do not have any recurrences. So firstly, I have this definition. Okay. A recurrence an equals c1, c2, and so on till ck. This is what is known as a linear recurrence. Okay, has a characteristic equation x to the k, and I put all the coefficients c1, c2, and so on, c2 k minus 2, and so on. Okay, this is what is called the characteristic equation of the recurrence. Okay, it's there in the lecture, so I'm not dabbling too much on it. And see the roots of equation. Okay, let me call it 1 is r1, r2, and so on till rk. Then what is an? An can be written in the following closed form: alpha 1 times r1 to the n, alpha 2 times r2 to the n, plus and so on. I can do root to the power n, the second root to the power n, and so on. Okay, this is how I can write, and this is my closed form. Okay, I'll just demonstrate it if it was not clear in the recap. Okay. So the question says solve the recurrence a n equals 2 a n minus 1 minus 25 a n minus 2, where a0 is equal to 4 and a1 equals 14. Let's try it. Okay. Given an equals 20 an minus 1 minus 25 an minus 2. Okay. I want to solve this. So according to the question, according to what we've seen earlier, the characteristic equation is what? It's x to the 2. There are two terms. Okay, k is 2. Okay, so x square minus x square minus 20x minus of 25 equals 0. Okay, so it's of this form now. You can see, right? So this can be written as x square minus 20x plus 25 equals 0. Now, what are the roots? Can we find the roots? Well, x equals minus b, okay, plus minus root over b square, which is 400, minus 4ac. 4 times 25 is 100, right? Divided by 2a. Correct? 4ac, yeah, divided by 2a. So now what do you have? We have 20 plus minus root over 300 by 2. This is what we get as the root. Okay. Now, what is root of 300? Root of 300 can be written as 10 root 3. Okay. So, which is equal to 20 plus minus 10 root 3 divided by 2. So, these are my roots. And what does my this say? This says I can write in terms of this form. Alpha 1 times root to the power and so on. So, an is nothing but alpha 1 times the first root, 20 plus minus 10 of root 3 by 2, okay, and plus alpha 2 times 20, sorry, this is plus minus 10 root 3 divided by 2. This is how I can write it, right? Now the question is, how do I find alpha 1 and alpha 2? Well, the good thing is I have my a0 and a1 given. So to solve this equation, I have on two unknowns, I know the value of two unknowns. Okay, and that is all I need, right? A0 equals 4, a1 equals 4. A0 equals 4, a1 equals 14. So what is A0? Oh, sorry, this is to the power n, right? So what is A0? A0 equals alpha 1 times 1, because it's power 0, right? Plus alpha 2 times 1. And what is A1? A1 is just alpha 1 times 20 plus 10 root 3 all to the divided by 2 to the power 4. Oh, sorry, to the power 1 plus alpha 2 times 20 minus 10 root 3 divided by 2. Okay. And what you do now? You just simultaneously solve both. So simultaneously solve both to get closed form. How? By getting from alpha 1 alpha 2. So you just simultaneously evaluate, you subtract, add, and so on, and then you will get your answer. Okay. So I mean this. For the sake of concept, I've just written it here. Okay. But I'll let you guys try the other one. Okay. So the question is, what is the solution of the recurrence relation? An equals 6, an minus 1 minus 9, 9 an minus 2. Okay. So what is the idea again? You find the characteristic equation. Step 1 is find characteristic equation. Step 2 is solve. And step 3, find alpha 1, alpha 2. This is the formula, 3-step formula. So let's find the characteristic equation first. So given an is equal to 6 an minus 1 minus 9 an minus 2. So characteristic equation, what is the characteristic equation? X square, okay, because there are two elements, minus 6x plus 9 equals 0. So can you tell me what the roots are? Solve this. Solve for x. So tell me what the roots are here in this case. Okay, this is 3 and 3. Let's verify. X equals b square minus 2ac divided by 2. B square is minus b, sorry, minus b plus minus root over b square minus 4ac. 4 9s are 36 divided by 2a, which is equal to 6 plus minus 0 divided by 2, which is equal to 6. But since it's a quadratic equation, it needs to have two roots, so both the roots are 6 and 6. Oh, sorry, not 6 and 6. 6 by 2, 6 by 2, which is equal to 3, 3. This guy says 3, 3. Yeah, that's correct. But so we found the roots. Okay. Now it's the same procedure again. Now we've done the characteristic equation. We've solved it. Now we want to find a1 and a2, alpha 1 and alpha 2. Okay. Okay. So first let's plug in. Okay. By the theorem that we have seen. Okay. By the theorem we've seen, we know that an equals alpha 1, okay, times the first root to the power n, okay, plus alpha 2 times the second root to the power n. Okay. Now what do? You find alpha 1 and alpha 2. Okay, given is alpha 0 equals 1, alpha 1 equals 6. Okay. Alpha 0 equals 1 and alpha 1 equals 6. A0 equals 1 and A1 equals 6. Then find alpha 1, alpha 2. So can you quickly do it? We need to use simultaneous equations for this. Or to make matters simpler, when n equals 0, you have a0 equals 1 equals alpha 1 3 to the power 0 plus alpha 2 3 to the power 0, and a of 1 means n is equal to 1, n equals 0, n equals 1 is equal to 6 as given in the question. Alpha 1 3 to the power 1 plus alpha 2 3 to the power 1. So now can you tell me what the answer is? So I have given in the simultaneous equation form. So now solve for alpha 1 and alpha 2. Can you do? call this equation 1. Let's call this equation 2. So won't there be an n with one of the coefficients if we have repeated roots? So won't there be an n with one of the coefficients if we have repeated roots? Well, why is it there? N with one of the coefficients. So you mean in one of the coefficients we need to put an n or something like that? Well, the theorem does not say anything for repeated roots. So I believe that it should not create a problem. Okay. Seems like you are correct here. Solution does end at that. Okay, let me just verify it. Yeah, that's right. Differentiation. Yeah, that's right. Okay. Thank you for pointing out that. That's right. It seems. Okay. So yeah. Okay. This one I'll try to keep it offline for now. Okay. So we'll leave it at that for now. So I'll try to confirm it offline. Okay. Or side by side. But what you pointed out is correct. It seems like since there are repeated roots, the same theorem will not work. Okay. Sorry for the confusion. There will be some kind of n factor. It seems like that. I'll just confirm and let you know. But in the meantime, okay, please look at this question. Okay, Divya, thank you for pointing out. Well, the question says in this time it's not the same. Why? Because there are three terms here. Okay, minus 3an minus 1, minus 3an minus 2, and minus an minus 3. And therefore we'll get three equations. So to solve them, I'm given three initial conditions. So what you have here is an equals minus 3an minus 1, minus 3n minus 2, minus an minus 3. And this time what we have is the characteristic equation will not be quadratic. Why? Because k here is 3. Okay, there are 3 terms here now. So the characteristic equation, okay, will now be cubic. That is x cube minus of minus 3, that is plus 3x square, minus of minus 3, that is plus 3x, minus of 1, minus of minus 1, that is plus 1, is equal to 0. So again, we need to solve for the roots, right? So can you solve for the roots? Can you tell me what x is equal to? I mean, there's a straightforward closed form for solving a cubic equation. Okay, could be complicated, but we could use some kind of factorization. Maybe try to think of an existing formula that would result in this particular equation, cubic equation. Okay. Minus 1, minus 1, minus 1, other roots. Yeah, that's right. So if we stare at it, okay, we'll realize the following fact. Okay, x cube plus 3x square plus 3x plus 1 is equal to 0. We'll look at a plus b whole cube. Okay, and what is a cube? A plus b whole cube. It is nothing but a cube plus 3a square b plus 3ab square plus b cube. Right. This is what we know. Now we realize that this particular equation is nothing but a cube plus 3 1x square, okay, 3x square 1 plus 3x1 square plus 1 cube, which is equal to 0. Right? Next, what we have is, we have that this is nothing but x plus 1 whole cube equals 0. This means that x plus 1 times x plus 1 times x plus 1 is equal to 0. This means that x equals minus 1, minus 1, minus 1. These are the 3 roots. But again, I believe that again the same technique will not work. Okay, sorry for the confusion right here. Same technique will not work because there are repeated roots. Okay. So here you need to, okay. So anyway, the same technique will not work because of repeated roots. I'll try to confirm offline, or maybe I'll attach a recording later on how to solve this, but I'll leave it for now. Okay, I'll leave it as like this for now, and record with the theorem that requires repeated roots. But I'll move on from now. Okay. Yeah. So anyway, now we'll look at counting using recurrences. Okay. So the question says the following. Okay. In how many ways can a 2x10 rectangular checkerboard be tiled using 1x2 and 2x2 pieces? Okay. The question says give the recurrence and initial conditions. So, okay, I'll draw it out for you. What it means is the following. So you have a 2 cross n checkerboard. 2, 3, 4, 5, 6, and so on. 2 cross n means that there are n columns and 2 rows. Okay, and you need to tile it. What do you mean by tiling it? Okay, and you need to tile it, okay, using 1 cross 2. Okay, I'll put 2 cross 1 also. Okay, 1 cross 2, 2 cross 1, and 2 cross 2 tiles. So what are the tiles like? 1 cross 2 means like this, 2 cross 1 is like this, and 2 cross 2 is like this. Okay, so to show that these are tiles, I'll just color them red. Okay, so what do I mean by tiling? I mean that tiling would mean covering all the board. So tiling would look something like, I'll tile this with a square board, this 2 cross 2. I'll tile this with a what do you call a 2 cross 1 board. I'm using this to tile it, and this one I'm using a 1 cross 2 tile to tile this. Okay, and if I tile it with 1 cross 2, then I'll need to tile it with 1 cross 2. But what I need is at the end, the entire checkerboard needs to be tiled. Tile the entire checkerboard using these tiles. Question is, give me the recurrence relation for this. Tell me how many ways there are to tile this. Okay, how many ways are there to tile this particular board using a recurrence relation, and give me the initial condition. That is what I'm asking. Okay, so for example, tell me what T of n is. Okay, where T of n is number of ways to tile an n cross, a 2 cross n checkerboard. Okay, yeah, so think about it for a while. Okay, if you come up with an answer, then very good. In either way, understand what the problem is. Okay, and try to think of how one might come up with a recurrence relation for this. Okay, okay. So I hope the problem is clear to everyone. Okay, there is a 2 cross n checkerboard, and I need to tile it using these tiles. So now I want to find T of n, but T of n is the number of ways to tile a 2 cross n checkerboard. So let me show the solution to you. Let's say this is your checkerboard, and this is 2 cross n. Okay, now let's say I had tiled, okay, let's say I had tiled this particular tile with a 2 cross 1 tile. Okay, these two boxes with 2 cross 1 tile. Then what do I have here? I have here a sub problem. What is the sub problem? Okay, the sub problem is tiling a 2 cross n minus 1 checkerboard. Okay, I hope it is understandable. The sub-problem is tiling a 2 cross n minus 1 checkerboard. If I know this sub-problem, then I can find a number of ways. Why? Because in this case, okay, there is only one way to tile this, and I cannot use a tile like this or this. A 2 cross 2 or a 1 cross 2 will not work. These will not work. So number of ways equals, there's only one way to tile the first, this way, okay, times the number of ways to tile 2 cross n minus 1. This is nothing but this. I hope you can see. Okay, this is the case 1. Now case 2, okay, is the following. I have a checkerboard. Okay, and this is 2 cross n. Now I'm tiling this part. How many ways are there to tile this? One way is using two vertical tiles, or the other way is to use a square tile. And how many ways are there? 2 ways to do this. And if you look at the remaining part, this is another sub-problem. But what does this sub-problem say? Sub-problem says the ways to tile, okay, n cross n minus 2. Oh, sorry, 2 cross n minus 2. Observe that this is n minus 2, because this time we are looking at 2. Why am I not considering this case? Okay, there's a mistake here. The case is this 2 horizontal tiles, not vertical tiles. Why am I not considering 2? This is also a valid way, right? To consider 2 vertical tiles. Why am I not considering this? Can anyone tell me? Why am I not using vertical tiles to tile these 2 blocks? Okay, well, why am I not using vertical blocks? Because this will boil down to the same case, right? Because case 1, okay, already deals with this. This case is already dealt in case 1. Because it could have been that, this I did with a vertical, and in this sub problem, I tiled it using a single vertical block. So I'm double counting, I'm over counting here. So I don't want to take into account the over counting. So therefore what I do is I do not consider this case. There are 2 ways, and how many ways are there to tile this? Number of ways to tile 2 cross n by n minus 2 is nothing but t of n minus 2. Okay, so number of ways in the case 2 is 2 times t of n minus 2. Okay, so total number of ways equals the number of ways in case 1, which is 1 times t of n minus 1, plus 2 times t of n minus 2. Okay, So that is your answer. Oh, but initial conditions, that is left, right? I mean, no recurrence can be left out without initial conditions, or you have an infinite evaluation. So along with initial conditions, let's say, or can you tell me the initial condition? Can you try what are the initial conditions? Let's say T0, T1, T2, something like that. What are T0, T1, T2 in this case, in the tiling problem? Okay, well, T0, okay, what is wrong? Okay, yeah. So T0 tells me the number of ways to tile a 0 cross, sorry, 2 cross 0 checkerboard. Okay, and what does a 2 cross 0 checkerboard looks like? It sounds absurd, right? You cannot have a 2 cross 0 checkerboard because the dimension, you cannot possibly hope to, you can, its height is 2, but its width is 0. So this cannot be done by the tiles that we are given. So number of ways equals 0. So T of 0 equals 0. Similarly, what is T of 1? T of 1 is number of ways to tile a 2 cross 1 checkerboard. What does it look like? 2 cross 1 looks like this. How many ways are there to use a vertical one? Use a vertical tile. I cannot use a horizontal tile for this. I cannot use a square tile for it. Now, what is T of 2? What is T of 2? T of 2 is for 2 cross 2 checkerboard. It is for a 2 cross 2 checkerboard. So what does a 2 cross 2 checkerboard look like? This. There are how many ways to tile it? Well, one possible way would be to tile it vertically by 2 tiles. Well, the other way to tile it would be horizontal tiles, or the other way to tile it would be using square tiles. So there are exactly 3 ways. So it is equal to 3. Well, you can actually verify it using the yeah, that's right, yeah. So you can verify using the recurrence relation also. That's right. So there are 3 ways to tile it. So T2 equals 3, and therefore you can try to form a closed form using this. Okay, using the methods that we specified earlier, but this is the recurrence for the particular problem. Okay. So moving on, we'll talk about a bit about asymptotic complexity. Okay. So the question is following. Okay, I have algorithms Okay, I have algorithms A1 and A2. Okay, and each take input size n. Okay, each take input size n. The question is, how much time does my algorithm take? What is an algorithm? Algorithm is just a sequence of steps. The question is, how many steps does it take for my algorithm to run? Okay. For example, I say, oh, okay, A1 algorithm A1 takes um, time 3n, and algorithm 2 takes time 4n. So at step 0 or step 1, it takes time how much? 3, and at step 1, this algorithm takes 4. So not much difference. And if you see the graph also, they do not have much of a difference. It almost goes parallelly together. Well, but if you look, so the growth is same. But if you look at algorithms like n and n square, the growth is not same. For example, we know that when we plot the first n, okay, it will become a straight line. Whereas if you plot the second one, n square, it will not be a straight line. It'll be a parabola like this. At some point, n square will keep growing, and it will grow so much. I mean, it will grow much more than it after a point. So therefore, at that point, we see that n square is actually asymptotically greater than n. Okay, so if algorithm 1 takes n time, 3n time, let's say, then it is of order O of n. We remove the constant for it. That is what we said. I'm just giving you a slight recap. Okay. And if algorithm 2 is of takes 5n square plus n time, we'd say it is of order O of n square. We remove all the smaller terms because this is dominant. Okay, this is dominant. Okay, so continuing. So let us look at the following recurrence. Okay, what is the time complexity of an algorithm of the following recurrence? T of n equals 2t of n by 2 plus order n. This is the question. And t of 1 equals 1. So, well, this is a recurrence for a popular algorithm. If you can simplify it and tell me also. So can you use substitution to show this? So can you try this particular problem? What is the complexity of the algorithm, which takes the following? The recurrence describes its growth as follows. Okay. Well, we use the same substitution method here. Okay, and the idea is that t of n, okay, t of n by 2, okay, can be written as t of n by 2 times 2, right? N by 2 divided by 2, or which is nothing but n by 2 square plus, sorry, 2, okay, order n. Okay, and then again this becomes 2 of t of n by 2 cube plus order n. Okay, here plus order n plus order n plus order n plus order n, and so on. And you can see the trend here that at some point it will be equal to some k. Okay, at step k, all these 2's will multiply to form 2 to the power k. T of n by, see, there are at step 3, there is a 3 here, okay, and there are 3 n's here, so it means 2 to the k at step k, okay, plus n plus n plus n k many times, so use kn. Okay, this is what we get. Now this process may continue infinitely, but our recurrence, okay, the intuition is that our recurrence will stop whenever we reach the initial case. According to the initial case, we need to reach at, according to the definition of recurrence, the process will stop only when we reach the initial step. So let's say we've reached the initial step. Say k equals 1. Oh, sorry, not k equals 1. Say t of n by 2k is equal to t of 1. Well, then what do we have here? Then we have that this means that n by 2k equals 1. And this means that n equals to the power k. Now find k, because we need to substitute k back here. K is equal to log base 2 n. Right. So what do you have here? You do 2 to the power k, which is nothing but 2 to the log base n, times t of n by 2, which is nothing but t of 1, plus kn. What is k? Log n, log base 2n. Okay, and what does sorry, kn, n log n, sorry. Something is wrong with, okay, n log n. Okay, and what is 2 to the log n? I mean, since bases are same, we know that this is nothing but n times t of 1, which is n times 1, because t of 1 is 1, plus n log n. And what is it asymptotically? Order of n log n. Okay, and so this is how you solve it using substitution. Okay, but if you see, this recurrence is also actually very familiar, because this is the recurrence for merge sort. Okay, this is for the partition process and this is for the merging process. So towards the end of the lecture, the merge sort was done. This is the recurrence for merge sort, and it takes time, roughly n times log n to work. Okay, that is the idea behind it. So yeah, I hope the idea was clear. Well, the substitution is very similar to the one we've done before. Okay, so yeah, let's try our hand at this question. Okay, which of the following options provide an increasing order of asymptotic complexity? Okay, so f1n equals 2 power n, f2n equals n power 3 by 2, f3n equals n log n. Okay, and one is missing, it seems. Maybe I've taken a note of it. Log n, and f4 of n equals n to the log n. So can you tell me what is the increasing order? Like towards the left you'll have the smallest growing function, and towards the right you'll have the largest growing function. Can you tell me which of these options is true? So which is the correct sequence in which the complexity increases? Okay, or in other words, okay, can you tell me which one of these functions grows the fastest? Which has the highest amount of growth among these four? F1, F2, F3, F4. Well, the answer is, the answer to which one grows the fastest is definitely F1. F1 of n grows fastest. It is exponential growth. Okay, cannot be. No polynomial can grow faster than exponential. So this is somewhat what f1 grows like, and f2 will grow like a polynomial. It will be always be slower. Okay, and you can take a very large example. I mean, I always find that to be the most helpful. So take a polynomial from here. Let's say n to the 3 by 2 and 2 to the n. Okay, and if you say n equals 10, okay, then you have 10 to the 3 by 2, okay, which is something like 10 times root 10, and root 10 is something like 3 point something, which is less than 30, which is okay, say around 30, whereas 10 to the 2 to the 10, what is 2 to the 10? 2 to 10 is massive, it's 1024. So at this point itself it's winning. Now we are further powering this 1024 by 2, and this is increasing therefore very slowly. So we already have that f1 grows fastest, so the f1 should definitely be at the right. Okay, let's try the others. Okay, so your answer should be something like something then f1. Okay, then let's look at n log n, okay, and n to the 3 by 2. Which grows faster? Now n to the 3 by 2 is nothing but n times n to the n times root n. Okay, and also obviously log n grows slower than root n. Well, how? I mean, you can try using. You can try. I mean, formally proving it is one thing, but well, you can always try to use large numbers to actually represent it. For example, say n is equal to some 2 power 10, okay, or 2 power 100 or whatever, then log of 2 power 10 is nothing but 10. Whereas, what is root n? Root n is some root 1024. Now, what is root 1024? We may try to calculate it. 1024 square root is 32. Right. So it's already beating it. So obviously root n is actually asymptotically greater than log n. And here you have a multiplier by log n, and here you have a multiplier by log n. Obviously, n log n is less than n to the 3 by 2. Now we have the final candidate. Okay, n to the 3 by 2 is gone, n to the n times log n is gone. We have n to the, okay, what did I just do? That's right, yeah. Next we have n to the log n. Where does n to the log n sit? That is the question. Well, let us compare it with n to the 3 by 2. Well, the bases are same, but you have one side log n as the exponent and you have 3 by 2. Let's just compare the exponents. Well, obviously 3 by 2 is less than log n in the long run. Okay, because 3 by 2 is 3 by 2, obviously. So if you plot it in a graph, then it will look like this. Whereas log n will slowly grow and go across, and it will go over 3 by 2 at some point. Or to make matters more understandable, say n is 10, okay, 2 power 10, then 3 by 2 is less than log of 2 power 10. Why? Because log of 2 power 10 is nothing but 10, and 3 by 2 is just 1.5. So we have that 3 by 2 is less than log n. Therefore, n to the log n, sorry, n to the 3 by 2 is less than n to the log n. Okay. So, because of this, we have that the smallest is n log n. Slightly bigger is n to the 3 by 2. Slightly bigger is n to the log n. And the largest is 2 to the n. So, what is n log n? N log n is f3. What is 3 by 2? 3 by 2 is f2. And what is n log n? N to the log n. N to the log n is f4. 3 2 4 1. So 3 2 4 1 is C. So your answer is C. So I hope that is clear to everyone. Okay, this is how you can compare different functions asymptotically, which means that which functions will grow faster and which functions will grow slower. You can compare them. Okay. So yeah, let's continue. Yeah, here you have another recurrence relation. Okay, using substitution method, can you tell me what the time taken by algorithm is? We said that the algorithm takes time this many. This is the number of steps it took. Okay, this is the recurrence relation. Tn equals t of n minus 1 plus 1, where t1 equals 1. Okay, and this is the initial condition. Using substitution, can you tell me what is the asymptotic complexity of the algorithm? So we saw a similar one for same word sort. Well, the idea is again is to keep substituting for the smaller and smaller values of Tn. Okay, so there is an algorithm who is described by this particular recurrence, and this particular Tn minus 1, okay, can be substituted by the same definition that we have already seen of Tn. So this is nothing but T of n minus 2 plus 1 plus 1, right? Because T of n minus 1 from this definition is nothing but T of n minus 2 plus 1. Similarly, you can keep substituting T of n minus 3 plus 1 plus 1 plus 1, and T of n minus 4 plus 1 plus 1 plus 1 plus 1. But what is this equal to? This is equal to 4 plus T of n minus 4. So after some key steps, okay, after some small key steps, T of n minus k plus k, T of n will be nothing but T of n minus k plus k. We reach this point. Now the only idea that remains is that the process is finite only when we reach the initial condition. So somehow we need to reach the initial condition, and the initial condition asks for the parameter to be equal to 1. So let's make this parameter equal to 1. Say n minus k equals 1. Okay, that is T of 1, okay, equals 1. Then what do you have? Then you have T of n equals, okay, and T of n equals T of 1 plus k. Now it's what is k according to this? K is n minus 1. Oh, sorry. K is n minus 1. So just substitute the value of k, we get T1 plus n minus 1. And according to the question, but T of 1 equals 1. So you have 1 plus n minus 1, and cancel these, and you get n, which grows in the order of O of n. This is the order in which it grows. Okay. I hope everything is clear. So in other words, this is also called linear growth. That is, this algorithm grows linearly. Okay, so the answer is B. So, so taking idea from this particular algorithm, this particular solution, can you tell me for this particular question? This time it's slightly different. We have a 2 out here. So how much of a difference does this 2 make? That is the question. Tn equals 2 of Tn minus 1 plus 1. Can you solve this particular recurrence? And tell me the order of growth for this particular algorithm. So I hope it's clear to everyone. It's quite silent out here. Um, just please let me know if something is not clear. Okay. Um, well, the idea is again similar. So Tn is just 2 times just substituted. Okay, Tn minus 1 is nothing but T of 2 times Tn minus 2 plus 1 plus 1. Yeah, which is equal to 2 of T of n minus 2 plus 1 plus 1 plus 1 and so on. Well, again at some step k, this 2's will multiply to give 2 to the k. Okay, T of n minus this will be 3, sorry, n minus k plus 1 plus 1 plus 1 and so on. How many times? K many times. There's nothing but 2 to the k T of n minus k plus k. Now again, the idea is simple. We want to reach the point T of T1. Say we reach point T1, which means n minus k equals 1, which means that k equals n minus 1. Well, if k equals n minus 1, we have that Tn is equal to 2 to the n minus 1 times T of 1 plus n minus 1. So this is nothing but 2 to the n minus 1 times 1 plus n minus 1. But asymptotically, what is it? Well, we need to remove all constant and the dominant terms, right? So this is the dominant term. So we should keep it and discard the rest. Also, it is multiplied by a constant, right? This is as good as 1 times 2 to the n plus n minus 1. So we don't need the constant also. This means it is of order 2 to the n. We'll just keep the dominant term here. Okay. In order notation, okay, in big O notation as it's called, we look at only the biggest growing term, keep only the biggest growing term, okay, and keep only the biggest growing term and remove all the coefficient of that term. Okay, for example, constants, yeah, coefficients of that term, which are constants. Okay, remove all the constants. For example, 1 by 2. If there was something like n, then we'll keep it. Okay, we need it, but constants don't matter. So we've removed 1 by 2, and then we've got this answer as order of 2 to the n. Well, what is the key takeaway is that 2 to the n and n are like miles apart in terms of complexity. Okay, they are miles apart in terms of complexity, and but you see the recurrence is very deceiving, right? This recurrence looks very similar to this recurrence. It's just this matter of 2 that is causing a problem. Why? Because this 2 actually indicates that the function is doubling, the algorithm or the function is doubling each time, and it doubles at an exponential rate. That is why you are getting this answer. Whereas in the previous case, it was not doubling; it was just adding one after the other. So right. So I hope that was clear. And yeah, again, please let me know if something was not. Well, finally, we have the last question. Okay. The question is as follows. There is a set of natural numbers S, all distinct, such that the size of S is n. Marie is asked, with sorting these numbers in increasing order, she comes up with the following algorithm. Okay. At step I of the algorithm, she finds the ith smallest number and places it in the ith position. Marie claims that her algorithm is better than merge sort. Okay. Remember merge sort from the we saw it before in this particular session also. Okay. Merge sort in terms of time complexity. Is she correct? So I'll give you an example. Let's say n equals 4 and 5, 7, 3, 1. So her algorithm is as follows. Okay, she finds the minimum and places in the beginning. Okay, and say it is 5, 7, 3. Does not matter. Then she finds the minimum again. Okay, say 3, and she places it at the ith position. This is the first minimum number. Okay, this is the second minimum, 5, 7, and the third minimum is 5. So it will remain like this: 1, 3, 5, 7, and fourth minimum is equal to 7, and it's placed at the fourth position. And then she sorted them. What does it mean to sort them? To arrange them. It is arranged in ascending order. That is what we want. Well, what Marie claims is the algorithm is better than merge sort. But we know that merge sort, okay, takes order n log n time. So is it true that this algorithm is better than merge sort? Can you tell me? Is this true that the algorithm that Marie has come up with, okay, is better than merge sort? So, well, the answer is as follows. Let T of n denote the time taken, okay, to place first minimum in first position, second minimum in second position, and third minimum in third position, and so on. Okay, and nth position minimum in nth position. This is how much time it took, right? Oh well, actually, there's a simpler way to analyze this, which does not even require a recurrence. Well, the simpler way to analyze this is she needs to go through each of the n terms, n elements, go through each of the n elements and place it and find the minimum and place it at position I, right? Or first position, second position, and so on. And how much time does it take to do that? Well, after going through, it takes n time to go through that. And next time she needs only go through the remaining, right? How many are remaining? N minus 1 are remaining. And next she just needs to go through the remaining, again, the final n minus 2, and so on until she reaches only one element. And she'll place the element there itself. And this is nothing but n times, if you know, this is the sum of series. So what is meant by the sum of series? This can be written as n times n plus 1 divided by 2. Right? And this is n square plus n divided by 2. In the asymptotic notation, it takes order n square time. Okay. And the other way to do it using recurrence would be, Tn will take something like Tn minus 1 plus n time. Because this shows that the remaining numbers you place for itself, how much time will you take? N time. And then you'll get something like n plus n minus 1 plus n minus 2 plus and so on till 3 plus 2 plus 1, which is you'll get the same thing. Well, is it better than merge sort? That is the question. Well, this is less than the time it takes for merge sort, which is n log n. And the answer is no. It is not better than merge sort. Okay, the algorithm that Murray came up with is not better than merge sort. I mean, if you've done like a elementary data structures course, then you may know this algorithm. You may know this algorithm to be what is called selection sort. Okay, this takes the minimum number and places at every pass. It takes the minimum number and places it at the correct position. So this is what is called selection sort, and it is not as good as merge sort. In fact, it is a really bad sorting algorithm, but it is a very simple sorting algorithm. Yeah. So with that we come to the end of this session. So in the beginning, it seems there was a mistake that I created, and I'm sorry for the confusion. I'll attach the correct solution for that, okay, with the recording that I'll upload. Okay, so please look at that part 2, and thanks to Divya for pointing that out. Okay, but we've come to the end of the session. Okay, if you have any more questions, please feel free to stay, and if you do not, then please feel free to leave. Okay, but thank you. So do let me know if there are any more questions. Okay, Divya and Regan. Otherwise, you are free to leave. Okay, thank you, Regan. Bye.
Thank you, sir.
Okay, thank you, Regan. Bye bye. Hi everyone. I want to make a clarification on questions 3 and 4. A student pointed out that the same theorem that we were using, okay, would not be working for this particular case because the characteristic equation that we find, okay, has repeated roots. Okay, so I want to make a clarification on how to solve it. So yeah, like she pointed out, okay, so the just to repeat the question says the following: find the solution of this recurrence equation, right? Recurrence relation, and these are the initial conditions. And we did all the steps, and we found the characteristic equation to be the following: 3, 3, and thus we have repeated roots. Okay. Well, because the usual theorem, okay, would tell us to do something like this, what is shown here. But in case of repeated roots, there will be an additional n factor out here. Okay, so let me show it with, excuse me, n color, sorry, n factor here, n times what was it, 3 to the power n. Okay, so the rest of the process is similar. Okay, instead of when n is 0, this entire term will become 0. This entire term will become 0. Okay, when n is 0, this entire term will become 0. Why? Because n, the factor of n is there and n is 0. So therefore what do we have? We have a0 equals a0 is nothing but 1, which is equal to alpha 1 times 1 plus 0. So this means alpha 1 equals 1. This is one of the solutions. And when n equals 1, we have a1 equals to, according to the question, a1 is equal to 6. Okay, and thus we have alpha 1 3 to the power n, okay, plus alpha 2 times 1 because of the n factor, 3 to the power n. Now what we simply do is, and this is equal to 6, and now what we do is n here is equal to 1, right, n here is equal to 1, and so we have 6 equals 3 alpha 1 plus 3 alpha 2. But what is alpha 1? Alpha 1 is nothing but 1. So 6 equals 3 plus 3 alpha 2. Which means alpha 2 is equal to 3 by 3, which means alpha 2 is equal to 1. Therefore, answer is an is equal to an minus 1. Sorry, what else? An is equal to alpha 1 3 to the power n, right? But alpha 1 is 1, so 3 to the power n, right? Plus alpha 2 times 3 to the power n times n times, because alpha 2 is also 1, 3 to the power n. So this is what we have, 1 plus n times 3 power n. This is my answer. So here if you see, the answer is C. So this is where the change happens. I'll explain it for the next question also. Well, we do the same circus. So here we are asking for a cubic characteristic equation, because there are 3 terms here. The characteristic equation will become cubic, and we finally solve it to get the roots as minus 1 minus 1 minus 1. Okay, and these are repeated roots. So for repeated roots, we follow a similar generalization, okay, to the one previously. So an will this time become, okay, an will this time become alpha 1 okay, minus 1 to the power n plus alpha 2, this time n, minus 1 to the power n plus alpha 3 n square minus 1 to the power. Okay, now the remaining procedure is same. Okay, a0, a1, a2 are known to us. Okay, a0 equals a1 equals a2 equals, what are the values? A0 is 1 minus 2 minus 1. 1 minus 2 minus 1. Okay, now when n equals 0, okay, when n equals 0, we have a0 equals 1, okay, from here, which is equal to let me make this simpler. This can also be rewritten as minus 1 to the power n, alpha 1 plus alpha 2 plus alpha 3 here n and n square. Okay, so that way I don't need to write -1 3 times. So yeah, so -1 whole to the power 0, okay, and alpha 1 plus 0 plus 0. This would mean that alpha 1 is equal to 1. Okay, we got the first one, first root. Okay, and next, when n equals 1, we have a of 1 equals -2 because of this. Yeah, a of 1 equals -2, which is equal to -1 whole to the power 1 1 plus alpha 2, okay, plus alpha 3, because n and n square both are 1. Okay, or you can do something like this. Okay, and therefore what you have is 2. Okay, I can cancel this off, equals 1 plus alpha 2 plus alpha 3, and this would mean that alpha 2 plus alpha 3 equals 1. Next, what we do is n equals 2. You know, a of 2 is equal to -1. Okay, now what we have is -1 equals -1 square, because it was -1 to the power of n, 1 plus, okay, now this time n is equal to 2, so it's n times alpha 2, so it's 2 alpha 2 plus n square alpha 3, so it's 2 square, which is 4 alpha 3. Now again the procedure is same. We have -1 is equal to this will become plus, and so 1 plus 2 alpha 2 plus 4 alpha 3, and 2 alpha 2 plus 4 alpha 3 is equal to -2, and alpha 2 plus 2 alpha 3 is equal to -1. Now take this to be 1, take this to be 2, using 1 and 2. Okay, we can subtract this from this, right? We get alpha 3 equals -1 -1, which is -2. Now this would mean that alpha 2 is equal to alpha 2 is equal to -1 plus 2 times 2, which is 4, which is equal to 3. Therefore answer is an equals to, now here we can substitute it. Okay, a1 is 1, alpha 1 is 1, so 1, okay, plus alpha 2 is 3, okay, and plus alpha 3 is -2, so -2 and square times -1 whole to the n. This is my answer. Okay, and which is B. Option B. Okay. I hope that the clarification was clear.